Hello, this is Math 1151, 4.9. This is a good section to attend because I don't know. I really have no idea. But I am convinced there's going to be a question like this on the exam, on the final, and or there should be an or between those, but maybe and on the quiz from this section. Okay, this is totally key. I don't see how we can go on without asking you a question from this section. So what's this section all about? Unfortunately, this is a difficult section. Antiderivatives. So we've been taking derivatives the entire time, and I sincerely hope that you guys are pros at taking derivatives. If you're not a pro, you know what you should do? You should send me an email. You should say, "Dear Bart, I am not a pro at taking derivatives." And then I will give you further instruction. Okay? Seriously, you guys have to be awesome at taking derivatives. I can teach you calculus if you can't handle fractions. I really can. I think so. 80%. I can teach you calculus if you hate algebra. Again, 80%. I cannot teach you antiderivatives if you don't know how to take derivatives. I will fail every single time. I promise. Not because I want to, but I just can't do it. I've tried. So you have to be a pro at taking derivatives. And what do you do if you're not a pro? Okay, practice is good, but at this stage of the game, you send an email to me or your TA and say, "Help, I am not a pro at taking derivatives. I need help now." It's hard to say. I'll email our TAs tonight and say, "Dear TAs, help me learn calculus. Bart, XOXO." That's kind of creepy. I won't do that. Okay, so now, so you should email them. And look, we're not going to think anything. We just want you to be able to do it. That's all we want. Antiderivatives. You have to be a pro derivatives. What is it? It's finding the function whose derivative is whatever I tell you. Now, you guys can already do this, I'm sure. Give me a function, so antiderivatives. So give me a function whose derivative is 6. 6x. Okay? Now, we have some notation for antiderivatives. And one notation is you do this. You say f of x is equal to 6. And then you can write capital F of x is equal to 6x. And you're supposed to think that you take the derivative of this one. Does that make sense? Can somebody give me another antiderivative for 6? 6x plus c, 6x plus 1, f of x equals 6x plus 4, 6x plus c, as this guy said, perfect. All these f prime of x, capital F prime of x, is equal to f of x in these cases. So yeah, you already know some antiderivatives. Now, the fact of the matter is that history does not, when we teach math, we typically teach it like, you learn this, and then you learn this, and then you do this. We teach it as if it's an uninterrupted march toward something, okay? In real life, it was much more confusing. And when they developed calculus, there were a lot of confused ideas. And only recently, fairly recently, have we put it together in a, quote, logical structure. But because of this, we have different notation. And so we have our notation, this capital F. And I like this, actually. I think this is pretty good. But we also have this notation that maybe some of you have seen before, or I know some of you have seen before. We could say, this means the antiderivative. You draw something like this, and you know what? I'm going to use a different colored chalk just to emphasize something. I'm going to use the hot pink here to emphasize something. Yep. Okay. Didn't have an eraser. That's what you have to do. So this is one piece. This thing here. And if I want to say the antiderivative of, and then I can say 6, and then this d thing tells me what the variable is. This is the antiderivative of 6, where x is the variable. And so this is going to equal 6x plus c. Now let me show you something. I like this idea. This is something, I just made this up. So now you do the antiderivative of, here, let's do another one. 2y d, and then I put the variable here. This is where the variable goes. dy tells you what the variable is. If we want, so what's the integral? Oh, sorry, this is also called the integral or the indefinite integral, just to be confusing. I'll try to say antiderivative every time, but I might say integral. What's the antiderivative of 2y dy? Y squared. And antiderivative is y squared, and then you can get all of them by adding in a constant if you want to, right? If I did something like this, and I don't want you to, if this makes sense to you, fantastic. If it doesn't make sense to you, I don't think we're ever going to try to trick you this way, okay? But I just want to show you one thing. If I did the integral, I just said it again. I said, okay, of 2y, and then I put an x here. What's the variable? X is the variable. So can anybody tell me an antiderivative of 2y? 2yx would be the answer here. That's exactly right. And so if this makes sense to you, that's fantastic. If it doesn't, you can sit on it for a while. We're probably not going to try to trick you with this sort of thing. It's just kind of, I'm trying to explain why we have this funky notation around. All right? And it might not even be talked about in the textbook, but I thought it was a pretty simple idea. Okay, so now, we know a bunch of basic derivatives, right? We know a bunch of basic derivatives, and from those derivative rules, we get our antiderivative rules. Do not memorize the okay, I'm not sure if this is a good idea, but I'm going to tell you anyways. I'm suggesting you don't memorize the antiderivative rules. They're bad. They don't work well. The derivative rules are awesome. They always work. The antiderivative rules, you have to think a little bit more. So if you know the derivative rules, you can say, how do I take the antiderivative? Then you run through the derivative rules in your head, right? You run through the derivative rules and you say, well, what's the derivative of this? What's the derivative of this? Oh, okay, okay. So let's see if we can figure out, as I say, don't memorize these. It's good to make yourself a chart and practice, okay? The other thing I worry about is, we just learned how to take derivatives, right? Yes. I don't want you taking antiderivatives when you're supposed to be taking derivatives. I don't want you to get confused which one is which. So I kind of only want you to really memorize one of them and then kind of use it slower the other way. Okay, let's see if I can, let's just make a big table at this point. So if I have the antiderivative of k, where k is a constant, dx, you guys already told me this is equal to kx, because the derivative of kx is k, right? This is kind of how when you should never, ever, plus c, right? You should never get one of these wrong because you can always check your answer. You can check your answer, just take the derivative, right? Awesome, awesome. Okay, so now, the antiderivative of x to the n dx is equal to, this is too hard. Stop for a second. This is too hard. I'm asking you a question that's too hard. Bad Bart. Okay? What's the antiderivative of, don't worry about it. I don't care. What's the antiderivative of x squared? Give me a function whose derivative is x squared. Don't think, just answer. X cubed. That's great. That's okay. He said x cubed, and I love it. Okay? He said x cubed, and I love it. So what we do is we guess. I want you to think about it this way. So maybe x cubed? Maybe x cubed? And you say, is this right? How do you know if it's right? Take a derivative. And we're pros. We are pros at taking derivatives. We are awesome at taking derivatives. So the derivative, well, d over dx of x cubed is equal to 3x squared. Is that right? No, but we're not that far off. And so we say this is just x cubed over 3 plus c, because when we take the derivative here, this 1/3, nothing happens to it. And this is what I'm talking about when I say know your derivatives really well, and then think about your antiderivatives. Know your derivatives super well, and then just kind of be more flexible in your thinking. Think about it, all right? Be willing to write something down and take its derivative and see if you're right. And if you're not right, just change. That's all I suggest you do. So what's this one going to be? So look, we have a guess here, right? What's this one going to be? Yeah, x to the n plus 1 over n plus 1 plus c, right? My Dr. Snapp endorsed method of doing this is if you see x to the n, just think x to the n plus 1. All right? And that's because here's a fact. Here's a fun fact about antiderivatives. Fun fact about antiderivatives, and I should write this over here. Fundamental facts. Okay, here's fundamental fact number 1. This is so fundamental that I'll just kind of forget it and just talk about it and just do it automatically. And that is the antiderivative or integral, it doesn't matter, of k f of x dx. You can always pull a k, a constant, outside, is equal to k times the integral of f of x dx. And that's what I'm trying to get at here. This 1/3 here that you're being concerned about, if you guess this, you're only off by a factor of a constant. And you can always adjust very easily. Maybe this doesn't quite make sense yet, but that's OK. So this is fundamental fact number 1. OK, so let's do another example. Let me just keep on pounding through our examples and see what can happen. We're going to see this done a couple times. OK, yeah. What's the antiderivative of e to the x? E to the x plus c, right? What's the antiderivative? This one's harder. This one's a little harder, but I'm going to write it down. A to the x dx. I'm not going to ask you. I'm just going to tell you. Equals a to the x over natural log of a dx. Oh, and how, oh my gosh, what am I doing? I'm being Bart's being crazy again. There we go, plus c. How the heck would you ever figure this out? This right here, this is true. I'll show you. I'll show you one way you could figure it out. That's really easy. It's good to make a list of antiderivatives. It's bad to memorize that list and try to use it really rigidly, all right? Because if you make the list, you're practicing things. That's the idea. So check this out. I want to know the antiderivative of a to the x dx. And I don't know this formula. I say, oh, geez, this seems really hard. Well, the first thing I'm going to do is I'm going to change that a to some other number, just to make it a little nicer for myself. So the antiderivative of 2 to the x dx. Don't pick e, because we know how to do e, right? Nobody would ever pick e. All right, so now, I don't know the answer. I don't know. But I can guess an answer. I'm going to guess 2 to the x. Who knows? Maybe it's right. It's clearly not right, but that's OK. So I'm going to guess that the derivative is what's the derivative of 2 to the x? Equal to. It's equal to 2 to the x. This guy told me natural log of 2. What type of thing is natural log of 2? This is a constant. And so my guess here is off by a factor of a constant. So what's going to happen is I should guess 2 to the x divided by natural log of x d over dx. And then when I take this derivative, when I take this derivative, what can I do with this constant? What can I do with the constant derivatives? I can always pull the constant outside, right? So this equals 1 over natural log of a times d over dx, 2 to the x. Aha! And I know what the derivative of 2 to the x is because that guy told me. 2 to the x natural log of 2. And then what's going to happen? Cancel, cancel. Right? So that's kind of where this came from. This is how I'm thinking about these problems. This is a good way to think about it. I promise. I know it might seem a little bizarre at first, but that's okay. Now, next one will be the antiderivative of 1 over x. And you know, this is equal to natural log of absolute value of x, to make my absolute value signs a little better, plus c. Now, I've already mentioned that this is a little bit misleading here because it's a little bit misleading. Yeah, please. It just leaves 2 to the x equals 2 to the x. So the derivative of this thing is 2 to the x, and we wanted to know the derivative, the antiderivative of a to the x. Does that make sense? We're going forwards and backwards, and this is a real easy time to get confused. Okay? So what you should do is you should do these things with a list of derivative rules in front of you. You should be thinking about derivative rules and remembering that you're working backwards. If you keep both sets of rules in your head, you're going to get confused. You're going to start applying them both. So what rules do we have? We have the derivative rules. Those are the rules we have. And then we think about the antiderivative ones using the derivative rules. Also, what happens to the exponent when you take a derivative? Goes down. When you take an antiderivative, it goes up. Derivatives are taking slope. Slope's a number. You're losing the x. That's sort of the idea. Okay. So let's see. 1 over, oh yeah, I said this is kind of misleading because while that is one antiderivative, there's lots of antiderivatives for functions. This is one of those hard things. There's lots of antiderivatives because, you know, another equally good antiderivative of 1 over x dx is equal to, say, natural log of x plus 4 when x is positive, and natural log of minus x plus 8 when x is negative. This is another antiderivative. This doesn't actually come up very much, but it's just something to kind of have. I can't imagine this is going to really come up, but I just kind of feel like I'm lying to you otherwise. And I try not to lie to you knowingly. All right. So, trig functions. What's the only derivative that I know? I only know one trig function derivative, people. Yeah, I know the derivative of sine is cosine. I know the derivative of sine is cosine. When I go to bed at night, I whisper that to myself. Derivative of sine is cosine, Bart. Go to bed now. If the derivative of sine is cosine, what antiderivative do I know? The antiderivative of cosine of x dx has to equal sine of x plus c. Outstanding. Oh, and what's the derivative of cosine? Negative sine. So don't write this. I'm about to write something down. Do not write it down yet. So that means that the antiderivative, don't write this down, of negative sine of x dx is equal to cosine plus c, right? Right? Now, what can I do with constants and integral signs? I can multiply. So I'm going to multiply both sides by -1 is what I'll do. And so that means that the integral of sine of x dx equals negative cosine. All right, so this is another thing we can put down. Boy, I have a big, long list here. Woo! Okay, so now think about this one. The integral of tangent of x dx is equal to, listen to this. This is crazy talk. I don't even believe this. I think this is just some place where I messed up, which I often do. Is equal to the natural log of absolute value of cosine of x plus c? Okay, I tell you this, you say, bull crap. How can we check it? What do? We just take the derivative. We take the derivative. Take the derivative, and so I'm going to compute the derivative of negative natural log of absolute value of cosine of x plus 4, because I hate having like random c's around. I don't know. Okay. Oh, okay. The derivative of natural log is the derivative of the function over the function, right? What's the derivative of cosine? Negative sine. So this would be negative sine of x over, cosine of x. And there's this minus sign here. Oh, and the derivative of this is 0. Oh, and these can't. This is equal to tangent of x. Is it okay? All right. And there's some more. We'll stop here with these rules. I could just start listing more of them, but there's tons in your book, and you guys know how to read. So what's the point of me just copying it down? It'd be better if I gave you some ideas of what's going on. So there's another fundamental fact about antiderivatives. Here it comes. Here comes the other fundamental fact. The antiderivative of f of x plus g of x dx is equal to the antiderivative of f of x dx plus the antiderivative of g of x. This is just the sum rule for taking derivatives. When you take the derivatives, you can take them term by term. You know what I'm talking about? You take the derivative of the one plus the derivative of the other plus the derivative. So you can anti-differentiate by these things. So let me show you an example of this. So let's look at an example of this. Here comes the example. The antiderivative of 7x to the 5th plus 42 over x minus 5 dx. All right? So this is equal to, this is the problem, this is equal to the antiderivative of 7x to the 5th dx plus the antiderivative of 42 over x dx plus the antiderivative of minus 5 dx. Cool? Because I can take the derivatives separately when I have pluses and minuses signs. Well, whatever. All right. Now there's something else. I can pull constants outside the integral sign if I want to. Now, to be honest with you, I don't expect you to show all these steps on an exam. I'm just doing it very slowly. I'd kind of like you just to go from here to the bottom line in one step. Okay? But we're going to do it nice and slow right now. So I can pull the 7 out, x to the 5th dx, plus 42 times the integral of 1 over x dx. Even this minus 5 can come out. That's going to be minus 5 integral. Some super sneaky people just write this. What does this mean? Integral dx. What? Yeah, and why is it x? Aha. She says, there's really a little 1 here. All right? But oftentimes they don't write the 1. And what's a very tempting mistake to think that what's there? 0. But there's really a 1 there. It's like 1 times dx is one way you can think about it. All right. So now, x to the 5th, we know what happens here. It's 7 x to the 6th over 6, right? Plus 42 times natural log of the absolute value of x, right? Minus 5, and the antiderivative of 1 is x. Again, I'm putting lots of extra steps in here. I'm just showing you how these facts work and how I'm using this. Plus c. At this point, if you've never seen this before, you shouldn't be so convinced. I told you the antiderivative rules are bad, and you should be saying, well, they look all right to me. Trust me, they are bad, and I'll prove it to you eventually. All right? For one thing, you can take the derivative of almost anything I throw at you. I think any function you write down, you can take the derivative of. However, if we went through the room and had you guys test me to see what ones I can take the antiderivative of, there's a high chance you'll stump me very quickly. For one thing, there is no formula for the antiderivative of something like sine of x over x dx. The best answer I can give you is, whose derivative is this? Oh, it's written like this. If you ask a computer for the formula for the antiderivative of sine of x over x dx, the computer is going to give you an answer that means exactly, well, you just find the function whose antiderivative is this. We don't have, there is no symbol. We just don't have it. That's kind of bizarre. We usually have symbols for things. But so there's no function that I can write down that's not an infinite series that will do this. Same way for antiderivative of e to the x squared. This looks pretty innocent right here. I cannot take its antiderivative. The best I can do is write this and say, okay, that's it. It's the function who, it's that. You can't do any better. And you might think, well, when would this ever show up? Well, you know the bell curve? It looks just like that. And so you're really kind of stuck. And you have to find some other way of computing the antiderivative that's not symbolic. That's weird. OK, so antiderivatives are hard for one thing. Now, this might not have looked so hard, but let's do another example. Let's do another example. That one's just like the one we just did. Yeah. Yeah, let's do this. How to guess some antiderivatives. Let's do it. I like this. This is the Dr. Snapp endorsed way of doing antiderivatives. When else are you going to get this? If you guys think this is total bunk, well, that's your opinion, okay? and you are entitled to it, but I think this is awesome. Here it comes. So if your integral looks like stuff prime times stuff to the n, if this is what your if that's what it looks like, then you guess that the answer is stuff to the n plus 1. If it looks like stuff prime times stuff to the n, now let's do an example of this. Example. Okay, here it comes. Example. X cubed over the square root of x to the 4th minus 6. Look, none of our rules help us out here. We are totally stuck here. Our rules don't help. How can we do this? Well, look. My eyes are skedaddling around, and this says x to the 4th. I see this x to the 4th here, right? And I see this x cubed. And I'm thinking to myself, well, I want to compute the thing whose derivative is this. And I know the chain rule really well. And the chain rule, what it does is it puts wait a second, look, how do we often rewrite this? To the 1/2. And in this case, it's to the minus 1/2, right? It's to the minus 1/2. So this is equal to the integral of x cubed times x to the 4th minus 6 to the minus 1/2. Aha, look. Does this thing here look like the derivative of this? Yeah. And is this raised to some power? Yes. So our guess for the antiderivative is going to be, well, if I follow my rule, it's going to be x to the 4th minus 6 to the negative 1/2 plus 1, which is to the 1/2. Now, how do I know if I'm right or wrong? I just take the derivative. So I take the derivative, d over dx. Oh, apply the power rule. So that's 1/2 x to the 4th minus 6 to the minus 1/2 times x cubed. Is that the right answer here? No, it's not the right answer. But can I make it the right answer? Yes. So everything's right except for this. But this is just a constant multiple. And I can always fix by constant multiples. And so my answer, well, whatever. My answer is 2 times x to the 4th minus 6 to the 1/2 plus c. Did that make it? Yeah, go, please. I have no idea. Let's see. It should be 4x cubed, which means these, which means these two numbers combine, right, equaling 2x to the 4th minus 6 to the minus 1/2 times x cubed, right? And now how far off are we? About as far off as we were before, except in the other direction. Now we just need to fix by this. So our answer is 1/2 times our guess plus c. And if you take the derivative of this, you'll see that we're right. You have a question, I think. Yes. He says, should your guess be stuff to the n plus 1 plus c? No, it should be stuff to the n plus 1. It should just make your guess as simple as you can. Since you can always add in constants at the end, you don't need to worry about it. Since you can always multiply by constant factors, you shouldn't worry about it. You should just write something down, take its derivative, and see what happens. Okay, I'm sorry. That's what I think you should do. We're going to learn other ways to deal with this. But to be honest with you, they're not that good. This is almost the best. You can get really far in this class if you know how to guess and check antiderivatives. I mean, you can just plow through things that would just stop other people because they're too focused on the microscopic technique. Okay, that's great. That's great. Oh, yeah, let me just point out one thing. If this is the stuff prime, here's the stuff prime here that I'm looking at. Okay? I'm just kind of pointing out the, yeah, what's up? To be honest with you, there's like no work to be shown for an antiderivative, is my opinion. Yeah, I mean, it's like literally you can just write it down. You could write, I'll guess this, take its derivative, boom. I was wrong, but now I'm right. You know, that's how it could work. So now, look, here's the stuff prime, and this stuff here, this is the, there's a stuff prime. That's what I'm looking for to use this. Okay, let me do another example. Still got plenty of time. Oh, yeah. The next situation that you might run into. Now, you're probably going to run into a polynomial. And it's going to have like sine and cosine in it. But this is good stuff. I'm going to show you one more. And then we'll do a bunch of examples from the textbook. And then we'll be done. Here's the next. I'm just going to show you this one more pattern here. Because this one occurs a lot. I'll show you two more, but I'll just show you one. I'll restrain myself. All right, here we go. If you have the antiderivative of junk, e to the stuff dx, there are two guesses you could make. You either guess e to the stuff or junk e to the stuff. Both are good choices. And you'll be almost, it might seem like this is way out of your way, but seriously, if you can think this way, you're going to understand the whole pattern. It's going to make more sense what's going on, I think anyways. Okay, so let's do an example. Example, here we go. The antiderivative of x e to the x dx. This is a tough integral. You know, how the heck am I going to do this? I'm not going to freak out. I'm just going to try to guess something. What are my two choices? I either guess x e to the x or e to the x. Which one's clearly wrong? Oh, I was going to say e to the x is clearly wrong. What's the derivative of e to the x? Is this e to the x? No, it cannot be fixed because x is not a constant. You can't multiply by x's, okay? You can only multiply by constants. So guess of e to the x, no. D over dx, e to the x is just equal to e to the x. So our guess is going to be x e to the x. And let's just hope that it works. Here we go. Because we're masters at taking derivatives, we can write this down really fast. X e to the x is equal to, okay, so let's take the derivative of this. What rule do I have to use? Product rule. E to the x plus x e to the x. All right. Now, how far off am I? I'm off by adding e to the x. I just subtracted off. So this is, so now, new guess. Guess one. 1, x e to the x. Guess 2, x e to the x. I see this here. Minus e to the x. take its derivative. Let's do it. d over dx of x e to the x minus e to the x. Okay, here I have to use the product rule, right? So this is going to equal e to the x plus x e to the x. What's the derivative of minus e to the x? Minus e to the x. What happens to these two things? Cancel, cancel. Equals x e to the x. Done. What's the answer? It's this right here. This is the answer. So our answer, because we found the thing whose derivative is x e to the x. So why is taking antiderivatives? I keep on saying it's hard. Why is it so hard? First of all, the product rule makes it hard. The product rule is difficult to undo. And the chain rule makes it hard. The chain rule is difficult to undo. And they always tell us as teachers never to write anything wrong on the board intentionally. But I'm going to break that rule today. I'm going to write something wrong on the board. So here, first I'll write wrong, 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 wrong. There we go. This is what I'm about to write. Is it right? No, it's wrong. Okay, so wrong, wrong, wrong. Okay, and let's see. Here it comes. The integral of f of x times g of x, oh God, I'm going to run out of room, dx, is not equal to, now see, I have a logical quandary, because I said it was wrong, right, equal to the integral of f of x dx times integral of g of x dx. You can't split it up by products. You will be tempted to do this. Please don't do it. All right? I mean, I'm not going to get mad at you, but we will count off. Okay? Even worse, you know? So, look, if we could split up the products, we could split this one up, right? And what's the antiderivative of x? X squared over 2, right? And what's the antiderivative of e to the x? E to the x. And then you could be like, oh, the answer is x squared over 2 times e to the x. Is that the right answer? No. All right? You can never do this. This is because we have to use the opposite of the product rule. So this is wrong. You can't do this sort of thing. Think about this. You will be tempted to do it. If you do it, that's okay. You can always check your answer. And how do you check your answer? Just take the derivative again. All right? Oh, wait, right. Okay, so let's do some problems from the textbook. Let's erase this wrong stuff I just wrote on the board. There'll be, if I was a betting man, I'd bet the textbook says something. Okay, here's the sort of problem. Here's a very likely sort of problem. So one type of problem we could ask you is, find the antiderivative of this. Find the antiderivative of that. We could ask you that. Here's another type of question that's very likely to appear on a quiz or an exam. It's called an initial value problem. I'll write that down. Initial value problem. Mathematicians love these things. I don't know why, but I do know that I love them. Okay? I look at these and I'm like, if somebody shows me a bunch of calculus problems, I'm like, boring, boring. Ooh, an initial value problem. Yeah, let's put that one on the exam. Okay? I don't know why. I like them. Okay? And most other mathematicians do too. Okay, here we go. This is number 68 on page 321. Here it is. This one looks awesome. G prime of x is equal to 7x to the 6th minus 4x cubed plus 12. G of 1 equals 24. And then you know what they want to know? They want to know what g of x equals. So they say g of x equals. I think we like this problem because most of the time, if you know what you're doing, they're not that hard of problems. But if you don't know what you're doing, then they seem a lot worse than they are. I think that's maybe why we like them. So what's the antiderivative? So how you do this, you find the antiderivative, and then you solve, you plug in this number here, and you figure out what the constant has to be. You find a candidate, because remember we have all those plus c's around there? So you just got to find out which, this tells you what the correct constant is. That is g of 1, isn't it? I don't want to be solving some other problem. Not that it really matters. Yep. Yep. Okay, so tell me an antiderivative of this thing. Plus c if we want to, right? Good? Yeah. Okay, and now I want g of 1. Oh, that's easy. G of 1 is equal to 1 minus 1 plus 12 plus c, right? This is equal to 1 minus 1 is 0, 12 plus c. And I told you this is equal to 24. So what's c equal to? C is equal to 12. Hard? No, not hard at all. Not a bad problem at all. This is the problem that you hope that you see. Let's see if we can make this a little worse. Here, let's do this one. This one looks terrible. Let's do this one. This is number 76 on the same page. V prime of x is equal to 4x to the 1/3 plus 2x to the minus 1/3. Okay, and v of 8 is equal to 40. Why did they pick 8? Because it's a perfect cube. You can take the cube root of it. That's exactly right. Okay, so now, what is the antiderivative of v? We should be saying, the correct way to say it, what is an antiderivative? Because there's many. So what's an antiderivative of v prime? What's v? What could v be? Guess. Just guess. Write something down. Don't try to do it all in your head. You might say, this guessing thing seems stupid, Bart. I say, no, because then you write something down, and as soon as you write it down, you can take its derivative and see if you're right. If you try to do it all in your head, I can't see things in my head. My head's dark on the inside. Okay? This is dark and empty. So now, this should be, what's 1/3 plus 1? 4/3. Awesome. 4/3. Plus, what's minus 1/3 plus 1? 2/3, right? So when I take the derivative, I'm going to need to have 3/4 around. So it's going to be 4 times 3 over 4. Yeah, perfect. Look, because when I take the derivative, what's going to happen? It's going to cancel, and we're going to get 4, which is exactly what we want. And so now I'm going to have 2 times 3/2. You see how I did that? You write something down. Don't do it all in your head. Write something down. Don't do it for me. Do it for you. Is this okay? Make sense? You're leaning forward, so I was just, oh, you can't see what my horrible handwriting wrote. Oh, no problem. No, I'm writing too small. You say, dear Bart, you're writing too freaking small. Write bigger so I can read it. I'm sorry. My apologies. So v of x, let's see if I can do a better job now. 4 times 4/3 x to the 4/3. No, seriously, I'm not, you guys are right, okay? To the 3/2 x to the 2/3? I don't even know anymore. Okay? But I think that minus 1/3 plus 1 is 2/3, right? So when I drop this down, I need these things to cancel. And on this one, it's backwards. Stupid Bart. 3/4. And so when I drop it down, I want it to cancel. Is it better now? I'm sorry. I forget. Just shout at me. Bart, this room's big. All right, so now we got to plug in. Oh no! We got to plug in 8. God. Okay. Plug in 8. So V of 8 is equal to, these cancel, 3x to the, 8 to the 4/3 plus, these cancel, 3 times 8 to the 2/3 plus c, and it's supposed to be 40, and all I have to do is find out what c should be. That should be 3 times 8, by the way. And, okay, 8 to the 4/3 might seem hard, but what's 8 to the 1/3? And what's 2 to the 4th? 16. So that's equal to 3 times 16 plus, what's 8 to the 1/3? 2. What's 2 squared? 4. 4 plus c. 3 times 16 is 48. And 3 times 4 is 12. So that's 48 plus 12 plus c equals 40. 48 plus 12 is 60. 60 plus c is equal to 40. C is equal to minus 20. And so your final answer, you should rewrite it. I'm not going to do that. I'm so sorry because time's up for me. But you should rewrite it and put the c and make it a minus 20 as your final answer. Have a wonderful weekend. It's beautiful outside.